Hello everyone and welcome to another episode of Continuous Improvement. This is a place where we dive deep into innovative strategies, tools and techniques to help you optimize processes, design smarter and work more efficiently. Whether you are an engineer, a designer or just someone passionate about making things better, then you are in the right place. Today we are tackling a topic that's reshaping the world of design: Topology Optimization. This method is transforming how we think about using materials, cutting costs, and improving functionality. So buckle up as we explore the potential and practical applications of topology optimization. So what is topology optimization? In simple terms, it's about figuring out where material is most needed in a design and where it isn't, so we can use less material without sacrificing strength. Imagine designing a car part that needs to be lightweight yet strong. With topology optimization, we identify the key structural areas, reinforcing only where it is essential. This technique is valuable in industries like aerospace and automotive, where saving weight and materials is crucial. For instance, companies like Airbus use topology optimization to design components that are light but durable, reducing fuel costs and emissions. In the automotive industry, BMW applies it to electric vehicle parts, maximizing efficiency and improving range by carefully distributing material where it counts most. Now let's take a look at the process of topology optimization. It generally begins with a CAD model, a computer-aided design that gives us a basic outline of the structure. Then an engineer inputs various parameters including constraints, loads, and optimization goals. Common goals might be minimizing weight, maximizing stiffness, or achieving a specific frequency response. After these inputs are set, a simulation engine applies algorithms, often based on finite element analysis or FEA, to analyze the design. This analysis tests how the material responds to stress, pressure, and other forces. It helps identify areas with little stress which can be reduced or eliminated to save material. Similarly, it reinforces areas that experience high stress to ensure structural integrity. At this point, it's worth mentioning that topology optimization can be iterative. The software might go through multiple rounds, continuously refining the design to meet all specified requirements. Some of these iterations are even automated, allowing engineers to focus on the other tasks while the program runs in the background. An interesting development in topology optimization is the integration of AI and machine learning. With these tools, the optimization process is evolving. AI can help recognize patterns in the material distribution across different design scenarios, learning which configurations tend to perform best. In other words, the more designs it processes, the smarter and faster it gets. Let's recall our examples that I have already said in this podcast episode. So, I gave you two examples. The first one was from the Airbus. Take the Airbus A320, for example. Engineers use topology optimization to design internal components like brackets and supports that are as light as possible without sacrificing durability. By shaving off just a few kilograms here and there, Airbus saves on fuel costs over the aircraft lifetime, making it more environmentally friendly and economically viable. The second example was related with the BMW. BMW has used topology optimization in designing components for electrical vehicles, like the i3 and i8 models, to reduce weight and increase efficiency. By strategically reducing material in certain areas, these vehicles can achieve better range on a single charge. Another field seeing fascinating advancements is biomedical engineering. Here, topology optimization plays a role in designing patient-specific implants, like hip or knee replacements. Imagine customizing an implant that fits perfectly into a patient's anatomy and is optimized for strength, support, and comfort. Using topology optimization, engineers can shape the implant to match the exact needs of the individual patient, often achieving better results than the traditional methods. Now you might be wondering, what are the challenges in topology optimization? Well, while the results are promising, the journey isn't always straightforward. For one, computational requirements can be immense, especially for complex structures. Simulations need significant processing power, which can drive up costs and extend development time. Another issue is manufacturing. Not all designs generated by topology optimization are feasible with traditional manufacturing methods like casting or machining. This is where additive manufacturing or 3D printing comes into play. By layering materials precisely where needed, 3D printing allows for the production of complex shapes that would be almost impossible to create otherwise. This synergy between 3D printing and topology optimization is a game changer, enabling designers to fully realize optimized structures in ways that were previously unthinkable. As a fun fact, even nature itself is a source of inspiration for topology optimization. Bones, for example, naturally adapt to become stronger in response to loads, distributing material where it is needed most. This concept of self-optimization is something we are just beginning to harness in engineering, but it's a powerful reminder of how much we can learn from the world around us. In wrapping up, it's clear that topology optimization is more than just a tool. It's a new way of thinking about design. By focusing on where materials are needed most, engineers can create structures that are not only functional, but also resource efficient and sustainable. As we look toward the future, topology optimization is likely to become a standard in engineering, as industries continue to prioritize the efficiency and sustainability. Whether you are an engineer, designer, or simply curious about where the future of design is heading, keep an eye on topology optimization. It's a field filled with potential, pushing the boundaries of what's possible in ways we are just beginning to understand. Thank you for tuning in to this episode of Continuous Improvement. If you enjoyed this deep dive into topology optimization, don't forget to like, subscribe, and share it with anyone you think would find it interesting. And as always, stay curious and keep improving.